Okay, class. Another topic in thermodynamics. So we have ideal gas. So this ideal gas is also presented in several parts. So this was also divided so that uh, the first concentration is on the ideal gas only. Okay, so we will not tackle processes here. So maybe next presentation will be the processes of ideal gas will be presented. Okay? So what is an ideal gas, class? So ideal gas is a theoretical gas composed of a set of randomly moving non-interacting point particles. Okay? So the ideal gas concept is useful because it obeys the ideal gas law and the simplified equation of state. Okay, so we have here several laws. So concerning ideal gas, okay? So we have the Boyles Law. So of course this was presented by Robert Boyle, or named after Robert Boyle. So this is 1627, 1691. So this Boyle's law states that if the temperature of a given quantity of gas is held constant, the volume of the gas varies inversely with the absolute pressure during quasi-static change of state. Okay, so that is what is meant by the Boyle's law. Okay, so this is the illustration of a Boyle's law. So we have the gas confined inside the container, and then at pressure 1 and volume sub 1. So if the volume is reduced to a certain amount, the pressure will also varies from its original pressure. Okay? So, the condition now is for constant temperature. The volume is inversely proportional to its pressure. Okay? So, inversely proportional, that is based from the Boyle's law. Okay? So, where the volume now can be written as B equals to C, where C here is the constant of proportionality over P, or simply P multiplied by B is equals to constant, meaning at any state points. So, from state point 1 to state point 2 or vice versa, the product of the pressure and the volume are always constant. Or, say, we can now write P sub 1, B sub 1 is equals to P sub 2, B sub 2 equals to constant. Okay, so where P, of course, this is the absolute pressure of the gas, and B is the volume of the gas. Okay? So we have also another law for ideal gas. Okay? So we have the so-called Charles law. So Charles law, of course, this was developed by Jacques E. Charles, 1746 to 1823. And, of course, the other is Joseph A. Gay-Lussac. Okay? So, this is 1778 to 1850. So, this law states that if the pressure of a particular quantity of gas is held constant, then with any change of state, So, from state 1 to state 2, the volume will vary directly. Will vary directly as the absolute temperature. Okay, so take note of that. If the pressure is held constant, the volume will vary directly as the absolute temperatures. Okay, so for another, we have B. So if the volume, so in this case now, the volume now is the one which is constant. Okay, quantity of the gas is held constant. Then with any change of state, the pressure will vary directly as absolute temperature. Okay? So, I think the law is clear. Okay? So, another. So, let us now write the equation. So, of course, for a constant pressure, the volume is directly proportional to the temperature. Or simply, B is equals to the constant of proportionality equals to T. Or simply, B over T is equals to constant. So, from state point 1 to state point 2, the ratio of the volume and temperature are constant. Okay? So, we can now write that as B sub 1 over T sub 1 is equals to B sub 2 over T sub 2. Okay? So, where? Of course, T is the absolute temperature and B is the volume. So, this is very easy. Okay? So, you cannot say that you cannot answer any problems here. So, I think it is very clear. Okay? So, we have here an example. Okay? So, take note, we have 3 laws to obey in this topic. So, first is the Boyles Law. Another is Charles or Gay-Lussac's Law. Or maybe, first is for constant temperature, another is for constant pressure, and another is for constant volume. Okay? So, let us now take this example. So, the temperature of 4.82 pound of oxygen occupying 8 cubic feet is changed from 110 degrees Fahrenheit to 200 degrees Fahrenheit. While pressure remains constant at 115 psia, determine the final volume. Okay, so let us now consider the equation. The ratio of the volume and temperature is equals to constant. Okay, substituting values now, the volume at 1 is 8 cubic feet, and then the temperature at 1 is 110, taking the absolute, so we have to add 460, is equals to the final volume over the temperature at 200 degrees Fahrenheit, making it absolute, plus 460 again, and the volume now at final state or state point 2 is equals to 9.26 cubic feet. Okay? So, very clear. Very easy. Okay? So, another we have here for the Charles Law. So, the illustration for a constant volume process. Okay? So, this is now the illustration. So, take note that the pressure is inversely or directly proportional to temperature, or the ratio of the volume and temperature is equals to constant. Okay? Okay. So, we have here also. Okay, so where, of course, P is the absolute pressure, PSI, kilogram per centimeter square, or kilopascal. So, the temperature is the absolute. So, maybe in Rankine or in Kelvin. Okay? So, this is now the general gas law equation of state, or the gas law equation, or general gas laws, okay? Or the equation of state. Okay, so wherein this equation is very simple. So this is PV is equals to MRT, where the product of the pressure and volume is equals to the product of mass, the gas constant, and the temperature. So take note again that P is the absolute pressure, V is the volume, and R is gas constant, and T is the absolute temperature, and M is the mass of the gas. Okay? So, and then we have here also the combined ideal gas equation. Okay? So, where P1V1 over T sub 1 is equals to P sub 2 over T sub 2. Okay? So, another example. So, we have here, what is the resulting pressure when 1 pound of air at 15 psia and 200 degrees Fahrenheit is heated at constant volume to 800 degrees Fahrenheit? Okay? So, take note that the volume in this problem is held constant. Okay? So, the equation now, so eliminating volumes from the combined ideal gas equation, that is now P1 over T1 is equals to P2 over T2. This is Charles and Gay-Lussac's law. Okay, so substituting values now, the absolute pressure is 15, the temperature is 200, making it absolute, plus 460, plus the final, or equals to the final pressure over the temperature of 800 plus 460, or the final pressure now is 28.64 psi absolute. Okay? So, another example. A volume of 450 cubic centimeter of air is measured at a pressure of 740 millimeter of mercury absolute and a temperature of 20 degrees Celsius. What is the volume in cubic centimeter rather at 760 millimeter mercury absolute at 0 degrees Celsius? Okay, so again, so this is a combined ideal gas law. So, meaning all the parameters involved changes. Okay, so the pressure now is 740. This is already absolute, multiplied by the initial volume of 450 cubic centimeter divided by the temperature of 20, plus making it absolute, plus 273, since this is I. Okay, so equals to P sub 2, 760 millimeter of mercury multiplied by the final volume divided by 0 plus 273. That's why we have here 273. Therefore, so the final volume now is 408.25 cubic centimeter. Okay? Another. Okay, so we have here several examples. Okay? A transportation company specializes in the shipment of pressurized gaseous materials. An order is received for 100 liters of particular gas at standard temperature and pressure, STP. Okay? So, that is 32 degrees Celsius and 1 atmosphere. Okay? So, what minimum volume of tank is necessary to transport the gas at 80 degrees Fahrenheit, maximum pressure of 8 atmosphere. So, take note. So, this is the problem in designing the tank or the pressure or the tank that will carry the gaseous materials. Okay? So, take note, this is the safest volume required. Okay? So, solution. So, from the combined ideal gas equation, that is P1V1 over T1 equals to P sub 2 B sub 2 over T sub 2. Again, substituting values, making pressure and temperature absolute, The final volume now is 13.72 liters. Okay, so take note, 13.72 liters only. Okay, so compared to the original or a volume of 100 liters. Okay? Thank you very much, class. Okay? So that ends my presentation.